Hello guys, in this video we are going to cover the information for the VSEPR theory and how to determine the molecular geometry of molecules based on their Lewis dot structure. So a super quick recap for the VSEPR theory. In very extremely simplistic terms, it just tells us that electron groups around the central atom are going to be the most stable when they are as far from each other as possible. This goes back to the idea that electrons are going to repel each other, and therefore, within the electron cloud, they are going to try and stay as far away from each other as possible. This, like I said, extremely simplistic terms, but just keep in mind we want to keep the electrons as far away from each other as possible. This is called the valence shell electron pair repulsion theory. So let's look at some terminology before we get started with the molecular geometries. So we're going to be talking about a lot in terms of electron domains. And what constitutes a domain is going to be the following. So here in the bottom of the screen, we have two different sections, electron domain with the bonds, the lines, and then the electron domain as the electron pair. So remember, the molecular geometry is going to be based on the Lewis dot structure of our covalent compounds. It will be determined, again, based on bonded and unbonded electron pairs. So right here at the bottom, we have one bond that constitutes an electron domain. Two bonds still constitutes one electron domain. Three, one electron domain. Four bonds, still an electron domain, which we really won't see that, so we'll just scratch off. And then also the lone electron pairs together as a pair will also constitute or make up one electron domain. So it doesn't matter if you're looking at one bond, two bonds, three bonds, or an electron pair, they all count as just one big domain. So let's look at a few examples. Right here on screen, we have phosphorus trifluoride. And very quickly, I'm just going to go ahead and draw its Lewis dot structure. We know that phosphorus is in group 5, so it's going to have a total of 5 valence electrons. And we know that each of the fluorines is going to have 7 valence electrons because it's in group 7. So I'm just going to go ahead and start drawing my fluorines all around. And hopefully we have been doing so much practice on this that it's becoming very simple for us to look at these type of problems and just be able to draw them out. So this is what our structure overall is. Now what we have here is the Lewis dot structure for phosphorus trifluoride. We have to look at the amount of domains that we have and how many lone pairs are on the central atom. Please remember, we are looking on the molecular geometry that is on the central atom. So we're just going to focus right now on phosphorus. So let's count how many domains this particular molecule has. There is a bond here with the fluorine on the left, so that counts as one domain. The fluorine at the bottom, that counts as another domain. The fluorine on the right counts as another domain. And remember, our electron domains can also be lone electron pairs. So we have another domain here. So we got 3 domains that are bonded. And we also have one domain that is unbonded. So now let's look at our chart. We are looking for a total of 4 domains, right? Because 3 plus 1 gives us 4. So 4 domains, but one of them is unbonded. So we're going to look down the list to the options that have 4 domains, but we're looking for the one that has one unbonded or one electron pair. So this would be right here. So the molecular geometry for phosphorus trifluoride would be tetrahedral trigonal pyramid, and their angles are going to be 109 degrees. Let's look at another example. We have H2S, so dihydrogen sulfide. So we have sulfur, which is going to be our central atom because it has a total of 1, 2, 3, 4, 5, 6. Has 6 valence electrons, 2 that can bond. And our hydrogens are going to have each of them 1 valence electron. So that's where we're going to form our bond. So right here we have a total of, let's count our domains. 1 domain, 2 domains, 3 domains, 4 domains. So we have 4 domains total. So we're going to be looking at one of these right here. And out of those 4 domains, 2 of them are bonded and 2 of them are unbonded. Right here, we're going to look at our chart, 4 domains with 2 lone pairs of electrons, and that would be tetrahedral bent with our degree angle about 109. Let's do one more example. We got silicon, oxygen, and 2 hydrogens. So here our silicon is going to be the one right in the middle. It can make a total of 4 bonds because it has 4 valence electrons. We have 2 hydrogens, which I already know are going to bond here. And I have an oxygen. So this oxygen is going to have a total of 6 valence electrons. So that's what I'm going to draw. And as you guys can see here, this is going to form a double bond because these two they have to have a double bond there in order to be able to have a full octet. So let's count our domains. We have 1, 2, 3. And remember, even if it's a double bond, triple bond, it still counts as one domain. You can think of them as also like sections that are stemming from the central atom. That usually helps when we look at the domains. So here we're looking at a total of 3 domains, right? And all 3 domains are going to be bonded because there is not a single lone electron pair on this silicon. I do know, and you guys can see here that on the oxygen, we got two sets of pairs, right? But those don't really count. We're only looking at the domains on the central atom. So those we are not going to take into consideration when determining what the molecular geometry for our molecule is. So again, we're only looking at the central atom and the bonded or unbonded electrons that it has. So here it has a total of 3 bonded and no unbonded. And again, that's on the central atom. So we're looking at 3 domains, specifically the one that has no electron pairs. So this particular molecular geometry will be trigonal planar. So hopefully you guys can see that our molecular geometry, in order for us to determine what it would be, is completely dependent on, do we know how to draw the Lewis dot structure? And can we determine the amount of domains and which of those domains are bonded and unbonded? It is also very beneficial for us to have this chart that is shown here on screen. For my students, you guys should already have access to your student resource handout that could be located on Schoology. But if not, it is available here on screen. Thank you guys so much for watching.